We now arrive at the last in our series of short presentations on set theory. Now, in the presentations so far, we've introduced the notion of a set and we've described what a set is. We've described how a set is defined by its members, and that is to say that any two sets X and Y are the same set just if they contain the same members. And we've introduced some terminology. We've introduced some symbolism, the symbol for membership. We've introduced the curly brackets within which the members of a set are set out to define a set. We've introduced a symbol for a subset and for a proper subset, and we've said that a set X is a subset of a set Y if and only if everything in X is also in Y. X is a proper subset of Y if everything in X is in Y, and moreover there are some things in Y which are not in X. We've introduced the symbol for the null set, the empty set. Remember, there's just one of them on the basis of the fact that sets are defined by their members. And we've introduced some operations on sets: the operation of union, the operation of intersection, and the operation of subtraction. Now, on the basis of those understandings and definitions, we are asked to prove certain propositions, and there are 6 of them on this page, and let's just go through them in order. First, we're asked to prove that the set X subtract X, because remember, for all of these operation symbols, any set X operation symbol Y, that string represents a set just in the manner that 1 multiplied by 2 is a number. So X union Y is a set for any two sets X and Y. So we're asked here to prove that X subtract X is empty. Well, X subtract X, by the meaning of subtract, is the set of everything that is in X and not in X. Well, for anything it's either in X or it's not in X. There is nothing that is both in and not in. And so there is nothing in this set, and if a set contains nothing, then it is the empty set, and the empty set is written like that. So that is quite simple to prove. Number 2, we are asked to prove that the set X union the empty set is a subset of X. Well, what is X union the empty set? It is the set of all things which are either in X or in the empty set. Well, the set of all things which are either in X or in the empty set are just those things which are in X, because there is nothing in the empty set. So X union the empty set is simply equal to X. So now we are asked to show effectively that X is a subset of itself. Well, any set is a subset of another by this understanding of a subset if the other contains everything which it contains. So X is a subset of any set Y if everything in X is also in Y. Question: is everything in X also in X? Yes, it is, and therefore X union the empty set is equal to X, and of course X is a subset of itself because it contains everything that it contains. Simple enough. I hope you understand this. I hope you're following it, because while expressions written out like this may appear at first sight to be rather complex, they are in fact, I hope this shows, extremely simple to prove if you break them down into bite-sized chunks and focus on the meanings of, in this case, these symbols. Okay, now number 3, we're asked to prove that if y is a subset of x, and moreover y is not the empty set, therefore y contains something, then x subtract whatever it is in y is not the same thing as x. Well, if y is a subset, in this case a proper subset of x, then x contains everything that is in y and then some. So let's suppose that y is the set, let's say, which contains a number of things including little y. Alright, and let's suppose, we don't know what little y might be, but it contains something because it's not the empty set. There might be nothing other than little y in this set. And let's suppose that the set x is the set which contains what y contains, so it contains all of these things, but because it's a proper subset, it contains something else besides, and let's suppose that that something else besides is this little x. It's a curly x, an italicized x, and that's what x is. Now, if that's true, what is x subtract y? It's the set of everything in x less everything that's in y. I'm going to put some dots there. And what is that? X minus y, in that case, is the set of everything that's in x, this minus all of this. So it is x and maybe some other stuff besides. Now that is not equal to that, because it omits all of that stuff. It is missing all of that stuff. So x minus y subtract y is not equal to x, because it is missing all of the stuff that's in y, which is in this set x. And that's a tick to show that we've completed the proof. Number 4, if x subtract y is x, then x intersect y is empty. What does that mean? X subtract y is the set of all things which are in x and not in y. Now, if x subtract y is x, then there is nothing in y that is not in x. If x subtract y with everything x with everything that is in y taken out of it is equal to x, there is nothing taken out of it. There's nothing taken out of x. So there is nothing that is in y and in x. And if there's nothing, then there's nothing. There's no x such that, I'm going to abbreviate that x is a member of x and x is a member of y. Now, if that's the case, what's x intersect y? It is the set of everything that is in x and in y, but we've said that there is nothing that is in x and in y. X intersect y is the set of everything which is both in x and in y, but we've said here by the definition, our understanding of the operation of subtraction, that there is nothing which is both in X and in Y. So this set is empty. There is nothing. And the set with nothing in it is the empty set. So that one's proved. Alright, now we come to number 5, and we're asked to show that if X union Y is X, then either Y is a subset of X or Y is empty. Well, let's take a look first of all again at this first bit of the proposition that we're asked to prove. Let's assume that X, I'm going to write it in a slightly different color just to differentiate it from the answer above. Let's assume that X union Y is equal to X. Now, X union Y is a set. It's the set, moreover, of all things which are either in X or in Y. But if everything which is in X or Y is just those things which is in X, then there is nothing, let's say no little thing, no little x, such that x, little x, is in Y and not in X. And little x is not in big X. Okay, now if there is no little x which is in Y and not in X, then Y is a subset of X. Now if Y is a subset of X, then everything which it does contain is in X, but then the empty set is a subset of any set Z. So Y might be empty, or it might be the case that it contains only things which are also to be found in X. So this bit is rather redundant. All we need to show is that if X union Y, the set of everything which is either in X or in Y, is just the set X, then Y is a subset of X. And one possibility is that Y is the empty set, because the empty set is a subset of every set, as we've discussed previously. Now our last proof, let me just give a tick to that to show that we've done that one. And now again I'll change color and come on to the sixth and last of our proofs. We're asked to assume that X union Y is empty, and on that basis to conclude that both X is empty and Y is empty. Well, X union Y is the set of everything which is in X or Y, but there is nothing in X or in Y. There is nothing in X, which is to say that X is empty. Let me just put that in red. And moreover, there is nothing in Y, which is to say that Y is empty. So if there is nothing which is in either X or Y, then both of those sets are empty.